Hello everyone, my name is Arindam Khan and these are video lectures for my course on design and analysis of algorithms. So let's start. In this course, I will assume you have already done a basic data structures and algorithms course. So you know basic order notations and data structures like linked list or stack or queues. I'll also assume you know simple sorting algorithms. I'll probably post some of the video lectures on some of these topics, but I'll already know you know about these things. So even if I talk about these things, it will be quite quick. In this course, we learn a lot of new algorithms and different design paradigms. And in this course, we'll also go over several new algorithmic paradigms like approximation algorithms and randomized algorithms. So let's start. First, let me start with the resources, the textbooks. As it's a classical subject, one of the most fundamental subjects in computer science, there are several good textbooks. For this course, I'll primarily follow this book. So I'll mention 5 or 6 textbooks and the pros and cons of each textbook. For example, the first book that I normally follow for the course is Kleinberg and Tardos. And this book is excellent. It has strong focus on problem solving and intuitions. It has very nice case studies and real world motivations. So if you're a beginner, this book is quite good. And it in a way it has less breadth compared to the next book, CLRS, and it has more focus on intuitions rather than the formal implementation. But I like more intuition over the formal pseudocodes. So it's one of my favorite textbooks. Second one is this book by Cormen, Leiserson, Rivest, and Stein, popularly known as CLRS. It's a mammoth, more than 2000 pages, very comprehensive coverage. It's a standard reference and it's also called Bible of Algorithms. There are many nice exercise problems, especially for data structures, things like heaps or binary search tree, AVL tree. There are very nice treatment of data structures. It's a bit dense, heavy. So in the beginning, you might not find it very friendly. It takes some time to appreciate. And sometimes the pseudocodes are complicated because they're focusing on the implementation details a bit more, which sometimes people might find a bit more confusing in the beginning. But again, it's an excellent textbook. So these are very popular textbooks. There are Indian editions available as well. The next 2 books I'll talk about. One is this new book called Algorithms Illuminated by Tim Roughgarden. It's one of my favorite books now. It's very clear, very intuitive. There is a conversational style of teaching. Tim Roughgarden is an excellent teacher. There are excellent video lectures for this course as well, and there are many practice problems. Relative to CLRS, again, the coverage is slightly less, and the textbook may not be available that easily in India. You can buy it from Amazon, but it's a bit expensive compared to the previous 2 books. Then the other book is, fourth book is Jeff Erickson's Algorithms. This book is completely free. I'll give you the web page link. It has it's very witty. It's one of the rare textbooks which is very witty with many stories and humor. So it's one of my favorite textbooks. It has deep coverage of many advanced topics like Metroids and several other topics which are not even covered in CLRS. And the exercises are again great for this book. Um, Negative side or cons, I mean, yeah, one thing is it's a bit advanced. So it is not the first algorithm textbook. So you probably, I mean, even the book in the beginning, the author says that it's probably the second textbook. It has less code and more ideas. So it's if you're mathematical maturity, this book is a great textbook for you. These are some companion materials for some of these textbooks. This is by um, Kleinberg and Tardos. On this web page, you will find all the slides for the chapters. Like the first chapter, I'll teach stable matching. The slides are there. And as I mentioned about the book by Tim Roughgarden, there are excellent video lectures on this web page, and there are many other materials for the course mentioned here. Similarly, for Jeff Erickson's book, the book is freely available. Again, this web page is there. All these descriptions I'll post in in Teams or also in the YouTube description section. There are two more textbooks. One is this book, Algorithms by Dasgupta, Papadumitru, and Vazirani. It's a very short book. It's a quick and yet rigorous theoretical introduction to algorithms. And this another book is by Sandeep Sen and Amit Kumar from IIT Delhi. It's an Indian and contemporary treatment of algorithms. It has chapters on streaming algorithms and other many interesting new topics. So out of these 6 books, you can choose the one that is your favorite. I'll primarily follow CLRS, follow Kleinberg Tardos. So this course is not a programming course, but I know many of you are interested in competitive programming and you might want to solve questions of algorithmic flavor from competitive programming. So these are some interesting books or materials you can explore. This is Competitive Programming 4 by Halim, and FND. It has a lot of nice questions from competitive programming competitions like ICPC and so on. This is another nice book by Laaksonen, again competitive programming, and this is a very nice web page called cpalgorithms.com. It's again a very nice textbook, and not textbook, it's a web page which has a very nice set of topics and problems. If you explore, it has many nice problems on these topics. To summarize, if you look at the books, if you have looking at coverage versus mathematical maturity, if you want short treatment, go for Dasgupta, Papadumitru, Vazirani. If you're just beginning, Kleinberg, Tardos or Tim Ravgarden's book is ideal. If you need more coverage, CLRS. And if you're slightly advanced and you like witty and conversational style of algorithm teaching, then Jeff Erickson's book is highly recommended. And also the competitive programming book can be useful if you like programming and want to solve algorithmic questions in competitive programming. There are several other video lectures which you can see. The Tim Ravgarden, of course, from Stanford. Now he's in Columbia, but I think it's from Stanford. These algorithms illuminated lectures are already online. You can go over. In fact, as I mentioned, I expect you to know basics of data structure. So many of these courses cover them very well. Another one is this course in MIT taught by Eric Demane, Jason Koo, and Justin Solomon. Excellent material. If you're looking for an Indian context, then IIT Delhi, Professor Navin Gaurkar has taught this course on data structures and algorithms. Again, excellent course. Please go over them. And there are several other YouTube videos on other topics. You are welcome to explore them. So let's start with algorithms. What is an algorithm? An algorithm is an explicit, unambiguous sequence of instructions usually intended to accomplish a specific purpose. Now you might ask, what is the first human invention? This is the algorithm for fire. So I asked ChatGPT to write an algorithm to start a fire. And it says, gather tinder, which are dry grass or leaves. Then these are to start the fire. Then to contain the fire, there is kindling, small twigs. And then you want fuel, which are larger sticks and logs. Then you place tinder in small pile. You arrange kindling into around timber in TP shape, like this kind of shape. And then you repeat this loop, generate sparks or friction heat until tinder starts smoking, and then blow gently on tinder. If tinder ignites, add larger sticks gradually and maintain fire with fuel. This is a step-by-step, unambiguous set of instructions which are explicit. And this was probably the first human invention. Let us see another example, which is cooking rice. In this case, we have some input, which is how many cups of rice we want to eat. We set water amount to be 2 times the rice amount. Then step 1, we rinse rice, and in this loop from I equal to 1 to 3, so you do it 3 times, you add rice to the bowl, fill bowl with water, stir gently, and drain water. Once it is done, you go to step 2, you prepare for microwave, you place rinsed rice in microwave safe bowl and add water amount to bowl, cover loosely with microwave safe lid or wrap, and then you go to step 3, cook rice and so on. So this is more a microwave recipe. You can ask ChatGPT about recipe for regular ovens. So if you compare this with algorithms, with computer science algorithms, we'll see there is similarity. There's an input. In this case, the input is ingredients like rice and water. Then there is hardware which is required, like oven and utensils in this case. And there is software, which is algorithm, the recipe. And by this algorithm, we get output, which is boiled rice. Now, as for a cook, what makes a great cook? It's a recipe. Similarly, what makes a great computer scientist? It's the algorithms. But in this course, primarily we'll talk about algorithms which are computational in nature, which is connecting math and computer science. But even this kind of algorithms, there is a long history. This is an example. This is a bone. It's called Lebombo bone. It was found in Lebombo Mountains in Swaziland. And this is oldest known mathematical artifact as well as computational artifact. It's a tally stick, and there are 29 distinct notches which were deliberately cut into a baboon's fibula. These 29 notches were counting the number of lunar phases. It's a counting artifact. And as we know, counting is a basic form of computing. So this is from 2000, 3000, around 3000, 40,000 years back, the first mathematical artifact as well as first computational artifact. So this also shows, though computers, the modern day computers are recent, but what came first, math or computing? Then we'll say that both were developed by humans as a way to reason about our physical world. Computing has an intuition, math has a rigor, and algorithms are connecting math and computing for the past 40,000 years. These are some other examples of algorithmic artifacts. This is Sumerian multiplication table from 2600 BCE from Sumer. And this is Elements, the famous book written by Euclid on geometry. Some fragments, papyrus fragments of this. In Elements as well, there was mention of one of the first prototypical algorithms, how to find greatest common divisors. So we'll start another algorithm with one more algorithm, which is more than 2000 years old, how to find whether a number is prime or not. So given a number n, whether it is prime or not, how do we find? So prime numbers are those numbers which are only divisible by 1 and then that number and no other numbers. So I asked ChatGPT to write a simple code, and this is what it wrote, a pseudocode, that given a number n, how to check its prime or not? You divide from 2 to n minus 1, 2, 3, 4, up to n minus 1. If n is divided by one of these numbers, then n is not a prime. You can stop. So how many divisions you are doing here? Roughly n minus 2, or let's say n, small n. Now, if you are slightly smart, if you think a bit, you will realize that if a number is composite or not a prime number, then its smallest divisor should be less than square root n. Same second algorithm, instead of dividing from 2 to n minus 1, we can just divide from 2 to floor of square root of n. And if one of these numbers divide n, then n is not a prime number. Now, if we look at the complexity of this algorithm, we'll see that input is n bit. So small n is the number, but the number of bits that we need to represent the number is log of. Think of if the number is 31, the number of bits we require in binary is 11111, 5 bits, which is roughly log of 31. So the runtime here we are getting in one case is n iterations, so 2 to the power capital N. Or even if we take this root n variant, then it's 2 to the power n by 2. Both are still exponential in input, which is capital N. So can you do faster? And by talking about the fast algorithms, we'll primarily talk about polynomial time algorithms. By polynomial time, I mean something which is polynomial in terms of input n. Or in this case, it's log n to the power, let's say 6, or some constant. So can we do it? It was a 2000-year-old problem. And only recently, in 2002, it was shown that primes is in P. You can find it in polynomial time. And this is done by Professor Manindra Agarwal, Neeraj Kayal, and Nitin Saxena from IIT Kanpur. At that time, Neeraj and Nitin were undergraduate students at IIT Kanpur, and still they were able to solve these 2000-year-old open questions. Now, algorithms in India has a deep and interesting connections. So the name, how did we come to this name algorithms? It has connections with India. So this is a Persian polymath, Al-Khwarizmi. He wrote a book, Kitab al-Hisab al-Hindi. Kitab book, Hisab computation, and Hindi Indian. So it was a book on Indian mathematics. And it was instrumental for spreading the Hindu-Arabic numeral systems throughout the Middle East and Europe. And this book was translated in Latin as Algoritmi de Numero Indoram. So the name Al-Khwarizmi was rendered as Latin algorithmy, and that led to the term algorithm. This procedural math, Indian math was very procedural. You want to find a solution step by step in a procedural manner, and that kind of math was known as algorithm. So it's slightly different from Greek mathematics, where the goal was more proof-based. You have a set of axioms and prove some statement, like Pythagoras theorem. In Indian mathematics, traditionally the goal was to find a solution computationally or procedural in a procedural way. These are some examples. So there are Sulba Sutras from 800 to 200 BC by mathematicians like Bodhayan, Apastamba, Katyayana. They describe a lot of algorithms like bisecting a line, drawing perpendicular, constructing squares and rectangles, and so on. A primitive form of recursion, dynamic programming, or divide conquer was found in the works of Pingala in Chanda Shastra from 300 BC. When I'll cover dynamic programming, I'll talk about this in more detail. So this was about history of algorithms, but what about in the context of modern day computer science? So these three people, I mean, there are several school of thoughts. First, I'll present the school of thought the proponents are Newell, Perlis, and Simon. All three are Turing Award winners from 75, 66, and 75. So their notion is that computer science is a study of computers. So computer is the central object and related phenomena like algorithms. On the other hand, we have Donald Knuth, who is known as the father of analysis of algorithms. So what does he say? He says computer science is the study of algorithms and related phenomena such as computers. What computer scientists have in common and that differentiates them from people in other disciplines is that they are all algorithmic thinkers. And I believe in this school of thought that the computer scientists have a unique way of thinking, which is algorithmic viewpoint. And that is what distinguishes the computer scientists from other disciplines. And as we know, modern day astronomy is little about telescope. Similarly, modern day computer science is not only about a computer or PC, it's far beyond that. And we'll see some examples. So why we should study algorithms? Of course, previous slide already talked about the importance of algorithms in computer science. It's more than a branch of computer science. It's basically the core of computer science. So if you are a computer scientist, you have to learn computer science, but also it's relevant to science, business, and technology. This is a quote by Professor Christos Papadimitriou that algorithmic lens is transforming the sciences, mathematics, physics, biology, economics, social science, and so on. Think of last year's physics and chemistry Nobel Prize. They are won by computer scientists. Next class, we'll talk about stable matching algorithm. Again, a Nobel Prize winning algorithm in economics. Biology has computational biology questions, sociology, how social networks, there are many computational questions in social networks, for example. So all these questions are now looked from an algorithmic viewpoint. And algorithmic thinking is transforming all these areas. Second is the applications. Think of the regular web pages that you visit, Google search, or YouTube or Netflix recommendations, Facebook friend suggestions, when you book flight or railway tickets, when you book a Uber cab, high frequency trading, photo or video editing, or any machine learning examples like linear regression or logistic regression, k-nearest neighbor, clustering problems. All these are algorithmic questions. And there are some algorithms like sorting, searching, which are everywhere. Even think of Google search. The algorithm is page rank, which makes Google unique. Or Google Maps. How do we find how to go from place A to place B? That's the shortest path application. Linear programming is omnipresent in many optimization problems. Machine learning is all about matrix manipulations. There are high dimensional objects which are matrices, and you're trying to learn properties of data by manipulating these high dimensional matrices. So again, matrix multiplication or a lot of matrix algorithms are are core in machine learning applications. So they are omnipresent. Algorithms are ubiquitous. Another reason is practical viewpoint, that most job interviews, they ask questions from data structures and algorithms. That's another reason that uh, to check whether you're a good computer scientist, they check your knowledge about algorithms. And there are several competitive programming or programming websites like Topcoder, CodeShare, HackerRank, and all these web pages. Of course, knowing the programming language and typing speed are important, but the core skill that you need to shine in this programming competitions or interviews is the knowledge of algorithms. And finally, I'll tell why I find algorithms so interesting. Because algorithms are beautiful and magical. This is a quote by Paul Edosh, and he was talking about beauty of mathematics. Why are numbers beautiful? It's like asking why Beethoven's Ninth Symphony is beautiful. If you don't see why, someone can't tell you. I know numbers are beautiful. If they aren't beautiful, nothing is. Paul Edosh believed that he did not know whether there is God or not, but he believed there is a book which God has written and it contains all the beautiful proofs. I believe there is a book, and Paul Edosh used to say the book is called, if the proof is beautiful, he will call the proof is from the book, the book. I believe there is a similar book for algorithms, and we'll see beautiful algorithms in this course, like stable matching or Kargar's min cut or quick sort. There is an inherent beauty. And I think as you learn about algorithms, you will appreciate the inherent mathematical beauty of this subject, why it's a magical subject. This also gives you an intellectual freedom to venture into the unknown. As CS is a relatively new area, many of the questions we don't understand completely. So even the simple question that we'll teach in the class, slightly some slight variants are completely unknown. I'll mention several of these questions. So one skill that one learns from studying algorithm is also to ask questions. So this is another quote by Ronald. He's back again. And he wrote this beautiful book called The Art of Computer Programming, which is also talking about art. Why algorithms or programming is also about an art. So if you have time, just browse this book. This is a very rigorous treatment of computer programming. So he says that I think the art of doing research consists of largely asking questions and sometimes answering them. Learn how to repeatedly pose mini questions that represent special cases of the big questions you are hoping to solve. So when you're solving a question and you are coming across an algorithm, you will always ask a question, okay, if I slightly tweak the algorithm, does it work? If I try it on this extension object, does it work? And this way, you will also get an idea to venture into the unknown. And that is really beautiful. Let me talk about two more related notions. One is complexity. In algorithms, we'll try to solve a problem. And complexity is a complementary part where it studies the inherent difficulties to solve a problem from a computational viewpoint. Some of the deepest questions in math is whether P equal to NP or not, whether verifying a problem is almost similar as proving a problem or not. And the notion of optimization is omnipresent when we try to find a best solution from a set of feasible solutions. We have to optimize. So when you try to minimize cost or maximize profit, then we come across these questions. Where to buy grocery, how to score more in math, which classes to take, how can we get more likes. These are all some variants of optimization questions. And in your job, you will again come across many optimization questions. Think of maybe you came across these two questions. You are dealing with some machine learning question and it has some matrix multiplication question. And you came across this question that you want to find whether given just 3 cross 3 matrices A and B, if there is a sequence of products A, B, something, which leads to 0. This is called Mortal matrix problem. Given two matrices A and B, you want to find if there is a sequence of them in a product, you will get 0. Or you can come across this question like TSP, where you are given some dots and your goal is to connect all the dots in the shortest possible loop. But both these questions are hard. Maybe you spend hours to solve these questions and provide an efficient algorithm or polynomial time algorithm, and then you're not able to solve. What can you do? The first trivial option is this. You go to your boss and say, okay, I can't find an algorithm because maybe I'm just too dumb. And that's not a reasonable solution. Probably you'll get fired. Second option is if you're lucky, like model matrix problem, you can show it's unsolvable. I can't find an efficient problem because it's related to halting problem and there is no such algorithm is possible. But most problems that we'll encounter in practice, they're in between. And for them, you have the third option. You show they're NP hard or they're hard as some other problem. Then you can mention, okay, I can't find an efficient problem, but neither of the smart people who try to prove P equal to NP, they could not find a polynomial time algorithm for a NP hard problem. So how can I find it? That's a valid solution. So to deal with such hard problems, algorithms can still help. For example, if you have an NP hard problem, you cannot, we do not have a polynomial time algorithm for all instances in the worst case. But maybe I'm happy if I find something near optimal in the worst case. And then we are fine with approximation algorithms. In some cases, we don't know the future data. Think of Uber cab allocation. So I don't know where the future request will come from, but still have to take a decision which cab to assign to a rider. That's online algorithms. In some cases, the questions are easy if some particular parameters, let's say the solution of the size of your solution is small, then the algorithm, the problem can be solved easily using parameterized algorithms in some context. Or if the input that you're dealing with, it changes over time, it's dynamic in nature, then dynamic algorithms can help you. If you're dealing with parallel computers or a distributed setting, then distributed and parallel algorithms can help. Randomness is another very powerful source in algorithm design. So we'll talk about this in randomized algorithms. That's another design paradigm. And then if you have limited memory, you can use streaming algorithms. If you want to use quantum mechanics, then there is quantum algorithms and so on. So depending on your problem, once you learn the basic algorithmic paradigms, the other advanced paradigms will help you to tackle your hard optimization questions. Now, the name of this course is Design and Analysis of Algorithms. So what is design? In the design, we write a pseudocode, how it works. And in the course, we'll not go for a programming language level implementation. We'll write a pseudocode which a human can understand. It's easier for the intuition. Now, to design an algorithm for a problem, the course will give us some hammers. For example, some general paradigms like greedy, local search, divide and conquer, dynamic programming, linear programming. So given a problem, we'll try to apply one of these paradigms one by one and see if it works or not. And for many problems, they're already helpful and we'll be happy to get a solution from these paradigms. Now, in the other hand, we have analysis, which talks about performance guarantee, why it works. Here we'll talk about complexity. So there are different computational resources like time, space, randomness, computation complexity. We'll primarily talk about time and space in this course, how much time and space is required to solve this problem by our algorithm. And then why the algorithm works, that's about proof of correctness. And for this, we'll use a lot of ideas from math, from combinatorics, graph theory, or probability, linear algebra. So this part is where math is required to give a rigorous provable guarantee. So with this, let me conclude. So for this course, what I need from you is care. Curiosity, you should ask questions, especially in the class or after the class. And second one is ambition. So apart from the regular homework, do something extra. Maybe do a project, read some research papers, implement something, or take part in competitive programming, and so on. So just do something extra, you'll have fun. Third point is R. You reflect and repeat. So it's a very deep subject. Sometimes just reading once, you will not appreciate the beauty. If you read multiple times, then you realize why some algorithm works and what are the pros and cons of different algorithmic paradigms, etc. From an Even if you read it, so I took my first algorithm course almost 20 years back, but even now when I read an algorithm, it's from an advanced perspective. I notice new patterns or new again new insights. So spend some time thinking about the algorithms, solve problems, and repeat. And last is very important is ethics. The work ethic, academic integrity, and perseverance. That's very important for this course. And what will you gain from the course? Again, you will gain care. C for CSS greatest hits. Algorithms is like classical music. It's really beautiful greatest hits from 70s and 80s that we'll learn in this course. And of course, I'll mention some in some cases the present day research frontiers. But it's just the introductory course. So we'll mainly learn about the classical algorithms, which are very beautiful. A, algorithmic thinking. The algorithmic viewpoint will help you in tackling with problems in any other area, from let's say economics to physics to chemistry and so on. Are about research problems. I'll mention several research problems or present modern day research frontiers when I'll talk about a problem. So if you're interested in research, this will give you opportunity to explore research problems. And finally is employability. If you are good with programming, you are good with algorithms, and it will also help you in getting a job. So with this, let me finish today's lecture. And next class, we'll start with stable matching, a Nobel Prize winning algorithm. Thank you.